good morning to everyone once again, and welcome to our last webinar. I present myself briefly, as most of you already heard my presentation. My name is Angelo Manfredi, and I am a researcher and a project manager working in engineering, Ingegneria Informatica in Naples, Italy. Previously, I worked more than 10 years in the same company as a project manager for Italian and foreign telecom sector customers. Since 2016, I have been in research and the development area, and since 2017 as a project coordinator for the European project Hyper360. Okay, let's start talking about the project essential. Hyper360 main result is an end-to-end tool set that allows to realize interactive 360 videos by adding interactive elements to 360 background video. Our consortium is composed by 8 organizations from 5 countries. The project received a fund by the European Union in 2017 and started in October of the same year to last 36 months. Now we are in the last month of the project. Okay, let's see briefly the project pipeline. The Hyper360 project final result is a toolkit that enabled the integrated production and the delivery of immersive interactive videos. An interactive videos is a video where the viewers can not only look in any direction, but also they can trigger interactive elements, for instance, audio, video, HTML5 panel, and so on, to get additional information or to jump to related interactive video. Capturing, post-production, and delivery are the 3 main phases of the Hyper360 pipeline. The pipeline is realized by using our suite of software tools. These tools are integrated and they can produce and deliver interactive video to play on standard web browser, smartphone, iOS and Android, and VR head-mounted display, for example, Oculus Go. Capturing phase. The tool for capturing can improve the capture high-quality video content and allow the recording 3D performance of visual characters. The project released 2 tools, an high-quality video content capture tool named OmniCap and a software tool, Caption, to record 3D performance of virtual character. We call them mentors, to be later fused in 360 interactive videos. The next phase is a post-production. Hyper360 project realized OmniConnect web tool that allows the adding of interactive elements to a background 360 video file in post-production. All interactive elements will be overlaid to the background video on the fly during the playback. Finally, we have the delivery phase. Hyper360 delivery is a cloud-based. As the content is streamed to lightweight players, it requires network connections. Currently, the content cannot be packaged to be downloaded for offline fruition. In this phase, we realized OmniPlay is a Hyper360 set of players for interactive 360 video playback that support all 360 Hyper360 features on all main devices. Standard web browser for PC, iOS and Android, smartphone, or head-mounted displays. OmniCloud is a Hyper360 internal support cloud service that delivers the interactive videos realized with the OmniConnect and hosts Hyper360 profiling and recommendation engine. Okay, thank you so much for your attention. Now I leave the floor to my colleague and friend Christian for the focus for the next presentation. Thank you.
Okay, and hello. I'm Christian Fuhr from Fraunhofer Focus, and I'm talking about the personalization options that we have in Hyper360. As Angelo already mentioned, we have essentially 4 basic layers that we are talking about in the Hyper360 project and which we have been working on. Since this is the 4th webinar, we're concentrating on the 4th layer, which is the delivery layer, and here specifically on the profiling and recommendation and also the automatic camera pass. I'm gonna introduce both of them and the reason for that now, and then leave it over to Dorothea from CERT and from Hannes from the UNEUM to go into more details about the tools themselves. Now, first question was, why personalization at all? Why do we care about that? And one of the things that's specific to 360-degree videos is that they can be overwhelming. In a 360-degree video, you're looking at a wider area than a normal fixed format video. If you are kind of out of luck, you look at in a scene and end up looking at a wall, there's nothing going on. And especially if it's interactive, there are buttons all over the place, playing audio, playing video, moving you to different things. And if you're not highly interested in the topic, but only kind of vaguely watching, you might get overwhelmed by the things that you have and that you can interact with. And in the end, that might lead to a situation where you essentially don't do anything at all and just leave it or switch somewhere else. One example for how overwhelming it can be is actually one of the examples that we are using as a prototype application within the Hyper360 project. If you have been to one of the earlier webinars, you might actually have seen that and seen that in action. It's in short a crime scene where a crime has happened and the viewer can kind of explore the scene, look at different things, try to figure out who did it and so on. And everything that's kind of colored dots and rectangles are interactive points. For most of the people in the scene, we have one button where the person talks directly to the camera and talks about the crime and what they've witnessed or what they're doing at the moment. The red one usually takes you to a different video where they explain what the specialist is doing, usually what the work area is, and the yellow ones here are generally leading to pictures of evidence. So if you click on that one, you see something about the corpse. If you click on that one, you see something about the footprint, and so on and so on. So essentially, if you're looking at the scene, it's about 20 things you can click on, in addition to being able to turn around, look at things. So for stuff like that, in general, some kind of help, some kind of support, some kind of recommendation would be useful. I'm a little bit vague about that in the specific example because from a content point of view, this is one where we didn't do personalization and wouldn't make any sense, because the idea behind the crime scene is to encourage exploration. So the idea is that users have to stumble around a bit, find out things about their own. If you have an actual recommendation system, which basically says, oh, by the way, there's a camera hidden in the back of the room, and if you click on this camera, then it will show you who committed the crime, and you don't have to look at any of the other evidence. That would be a good recommendation, but it would kill the experience in this case. So for this specific case, we didn't use it, but it's a good example why it's useful in general, just for getting oriented in 360 degrees. And the other quite obvious thing is a commercial benefit. If you want to sell something the same that basically every video service does, that also shopping service does, they present you stuff that you're most likely to be interested in. Also, once again, in the connection with the fact that 360-degree videos can be overwhelming. So, for example, take something like a shop. You enter a shop, like an electronic shop, and it has all kinds of stuff. And if you go there, it's lots and lots of things, and you don't really know what you want to look for first, or what's going to be interesting. If you know something about the user, for example, if you already know users are interested in Samsung devices, maybe because you detect that he's using the Samsung device or for previous behavior or stuff like that, then, for example, you can just hint going at the corner and saying, by the way, you might want to look at these things first. Of course, the user can always look around on their own, look at things they're interested in, saying, oh no, actually, at the moment I'm looking for PlayStation games, but at least it helps to give some kind of initial thing, some kind of initial entry point. And one of the very nice things about 360 degrees, where we also have to say there are things that are different about 360 degree videos from general recommendation, because of course recommendation has been done before and there are good solutions, but the interesting thing with 360 degree, we don't have only the clicking behavior of the user, which is the one you got normally, where you essentially see what does the user interact with and then react on that. But you can also see where the user is looking in the 360 degree videos, and you can assume that if a user looks at some specific point in the 360 degree videos for a couple of seconds, that might be more interesting to the viewer than something where he basically just glances over. So this is additional information that we can use in 360 degree videos, and that's kind of specific to Hyper360 to deal with it. And one example where we use that recommendation is essentially kind of media selection, media recommendation thing. We have a 360-degree tour through the RBB studio. RBB is a broadcaster in Germany, and there's a studio with a little couch where they give a presentation and then show videos from there. And once the user gets into this room in the studio, then he can see different things that have been produced in the content of the broadcast. And since the broadcast is a long-running one, there's really hundreds or thousands of individual presentations, and the idea is here, if you are select one or two of them, then presenting more of them the user might be interested in. And that's not only by putting them in the center of the screen, but also dealing with stuff like size and transparency. So things that are less interesting might be more transparent, so a little bit more hidden. Things that are more interesting going to be larger and going to be more opaque and stuff like that. So these are the ways we using it. And one of the things that is relevant because there are essentially or in most cases, there are two ways to do recommendation. One of them is really just following user behaviors of lots and lots of users, and basically know if a user clicks this one, this button, and 90% of the users do that, and a new user comes and presses the first and the second button, then you know, because 90% of users have clicked the third element after that one, that might be recommendable. The disadvantage of this is obviously you need lots and lots of users to have consistent behavior that are useful for prediction. And the moment you put in something new, like a new element, a new button, then essentially your data you got before this is pretty much worthless. The other big start, and that's also the one that usually used for media recommendation, book recommendation, and goods recommendation, is an ontology based. So you associate the individual buttons with terms, with tags. You associate the individual elements that are selectable or could be recommended by terms and tags. Then you try to build a connection between those, and based on these connections, then you make the recommendation, which has an advantage. You need less information. You can actually work with just one user going through that and still be able to do recommendation without having millions of users of the tool. And the other advantage of that is if you have a new item, if the new item have sufficient useful tag information, then this icon will be recommended even if it's never been selected by anyone before. And about all the recommender and the Lumo engine behind the ontology used and all these things that Dorothea from CERT will tell you about in about 2 minutes. And after that, that's the other thing that we have to make 360-degree video a little bit more presentable for people who don't really want to handle 360-degree. And this is actually the extreme form of doing that. That's basically taking a 360-degree video and generating a traditional video from that one. So viewers don't actually interact with the video at all, but the video is transformed in a standard video, and then that one can be watched. It's also helpful if you have an older TV set or device that doesn't work with 360-degree videos. Then you can have one 360-degree recording, and based on this 360-degree recording, then you can just generate a normal video and use that one. What we have been using, for example, is a concert scene where the 360-degree video, and we also applying it. That's something Hans is going to tell you about after Dorothea has been talking. Then we use various parameters, various rules to generate a normal video from that, partly based on motion, where's the most action, partly made on video rules, like not staying too long on one thing, not basically moving against the flow of performance, and so on and so on. And then we generate the video out, or normal fixed frame video out of 360-degree video. At the moment, I have to say, we're not doing that on an individual recommendation base because the process takes some time. So at the moment, we're having a very dynamic set of rules, and then basically apply those rules, let the whole 360-degree video run to that, and then having a normal fixed format video at the end. But these kind of things, the rules are flexible and could be influenced by recommended by individual preferences. So what we could do at the moment is let the individual preferences go into the rule system, then use this rule system in an offline process to generate a video in fixed format, and then the viewer can see it, but we can't do it in real time right yet. So we can't have a direct experience, but technically and conceptually we are able to do that.
Okay, hi. Thank you, Christian. So hi, I'm Dorothea Tatsu from the Information Technologies Institute of the Center of Research and Technology, Hellas, in Thessaloniki, Greece. And I'm going to go into more detail about what Christian just introduced about the semantic interpreter that interprets miscellaneous and heterogeneous content under a homogeneous vocabulary, homogeneous ontology, and the recommendation engine that is used in the project to recommend items within a scene or among different media to the users based on their personal preferences. So about the ontology that Hannes just introduced, we are using the linked user model ontology. Ontologies basically are shared conceptualizations about the world. So they try to model what actually stands true in the world, like the sun always comes up from the east and always sets from the west. They define the vocabulary, the syntax, the grammar that you're going to use to make some statements about what stands true in the world or in your specific domain, and they provide those particular statements that you need to make some logical inferences about what's going on inside a domain. So Lumo is a mid-level ontology, which means that because we had a lot of things to deal with in our domain, like what annotators or media producers use to characterize the content that they want to produce and give out to the world, we needed to think about coverage, and we needed to cover a lot of concepts and a lot of relations among those concepts. But we also needed to make the ontology lightweight enough to make it tractable, lightweight, slim, and able to be used by logical inference services like the reasoner that we're using for recommendation. So this is a trade-off that we did, and the ontology models all aspects that have to do with networked connected media, but from the user perspective. So it models information about the content descriptions, the content metadata, but it also models other meta information like space and time, location and time that the media has been published or can be found, and information about the media types, but also information about the user and their location and time situational condition. It is publicly shared in the link that you can see in my slides under a Creative Commons license. So what does Lumo model? Like I explained, we have the spatiotemporal information, which is about space and time of the content items, of the media items, but also of the user itself, themselves. The context dimension, which again have to do with the context of the user, like who he's watching the media with, any other information about the user, or the context attributes like about the content itself, like the media type, the metadata, the type of metadata media has, etc., etc. We also have a high-level agents subcategory, subhierarchy that deals with people and organizations that can be characterized in the content descriptions, but also about people and organizations that have to do with publishing or viewing the content. And then we have the content-specific, the domain-dependent dimensions, which basically are all the information, all the concepts and the relations that might be used by an annotator or inside the media item itself to characterize the content, like what it is about, what's the topic, what it deals with, what objects you can find in there, what products you can find in there, what abstract notions can be found inside the content, etc., etc. So Lumo is an ontology that we've been developing for the media domain for several years throughout several European projects. It's now on version 4. And it models over 1,000 concepts about the media items, about the content, and about the users. Over 35 relations and over 2,400 axioms, rules that show some kind of correlation between the concepts and the relations. Those rules might be hierarchical or non-hierarchical. So what do we do with this ontology? We use it to homogenize the content descriptions and the user situational context by using trained lexical graphs that may pertain of keywords or words in general that can be found in the metadata or the descriptions of an image, a 2D or 3D video that is embedded inside the content, whatever that has to do with the content, under this very structured, very specific vocabulary that we're using, ontology that we're using, namely LUMO. This is also something that we've started a while ago in another project about interconnected media, but what we've done now, except for some other optimizations, is that we've rendered the methodology multilingual. Right now we support English, which is the primary language that LUMO is written in, German and Italian, but the method is expandable to any language that anybody wants to use, because we use, based on the BubbleNet API, which is a very, very common and well-known and free mostly tool for natural language processing that may give you synonyms in any language to the concepts of the LUMO ontology. So what we can do is now, in more than one language, homogenize all the words, all the keywords that are found to characterize a content under LUMO, the common vocabulary that we use for inferring what the content is about and what the user wants. And so this homogenization, semantic interpretation process is used in both homogenizing the preferences that the user might have that we understand implicitly, like Christian presented, based on how the user consumes, how the user behaves when viewing a 360 video, like clicking inside embedded objects embedded inside a 360 video scene, or focusing on specific areas inside the 360 video scene. And also, again, we use it in the recommendation engine in order to interpret and homogenize all the content, all the candidate content that we want to recommend inside the 360 video before we do the semantic, before we do the matching between the user profile and the candidates inside the video. An example of what I mean by interpreting, classifying, homogenizing content under the common vocabulary is that, as we can see, different media items with different media type items, like for example, on the left in the slide, you can see a video from YouTube, are either annotated or automatically characterized by specific keywords. Here on the video on the left, you have the artists and musicians that take part inside this video, and some other information about what this is about, what this video is about. So it's from the Rock and Roll Hall of Fame induction. It is an entire ceremony. It's a live performance, etc., etc. On the right, you can see an image from again, a music-related web page. You have a title for the image that tells you something about what it is about. You have some meta keywords again, and you have a description that tells you what this image is about, what it pertains to. So these are all very differently formatted information of different contexts, different vocabularies, different whatever, and we want to homogenize them under something that we can make sense of. That's something that is slim in structure that we can make sense of and can make inference from. So on the left, you can see a potential semantic graph, lexical graph, that pertains in the blue nodes of the concepts inside the LUMO ontology. And in the white nodes, you can see all the miscellaneous words that might be related to these concepts from the ontology. So in these white nodes, you can find several words that are in the keywords of the YouTube video example that I showed you before. And based on their correlation with the LUMO ontology concepts, we can understand, we can slim this down, or if it's too small, you can see later on in my demo, we can enrich it a little bit, to 4 in this particular example, very specific things that this video is about. So it's about music. The first and foremost thing that we want to know, the topic of this particular content item. It's about rock music in particular because it says so in the description. It is about a concert, and there's a bunch of musicians on it. Beside on the left of the 4 ontology concepts that this content item was classified to, you can see a weight. This is from 0 to 1. It pertains to the confidence of how much we're sure that from what we've done in the automatic, from what we found in the automatic process, that this is actually what this content is about. So yeah, as I said before, this information is used to understand and interpret semantically the user preferences based on what the user clicks or views inside the 360 video scene, or if we're talking about interconnected videos from the entire video or the entire 360 video or any type of video. And we also use it to, let's say, get a list of the items that we want to recommend to the user and use the recommendation engine that I'm going to right now to match the candidates to the user preferences. So what we use as a recommendation engine is a logical or semantic reasoner. So reasoners are tools that, based on particular statements and premises of what is going on in the world, what we know for the particular contextual situation, and what we have as facts in the particular situation, they try to make to conclude to logical consequences of what actually holds true at the particular moment that we're examining. So we're using the Life Reasoner again. This is a tool from Surf that is open source, and you can find the link that I have here. What the recommendation engine through the reasoner does is to determine how much a user prefers or not, or that they're really not interested in a particular content item that is found in a scene. So what can be found in the scene of the 360 video, especially in the Hyper360 case, might be 2D or 3D videos like the method that you saw in the webinar, in the last webinar. Hotspots, embedded hotspots, links that can link to external web pages, images or text within the 360 scene or the entire video. It can also pertain to what's going on in a series of interconnected 360 videos, but basically you can use this recommendation engine and this method to try to understand what the user prefers for any type of media that has textual metadata attached to it. So what the reasoner does is it performs semantic matching between the user situation, the user preferences, and the candidate's recommendation items. What it does at the end is to assign a preference weight to each candidate content item based on how much it feels the user prefers this or not, or it indicates explicitly if it's something known from the user profile that the user really does not want to see this particular type of item. So a very slim example of how this works. On the left, we have what we actually know from the ontology. What stands in the world is that a concert is a music event. A festival, again, is a music event. A music event is an event in general. Music events always have topic, are related to the topic music, and musicians are always also related to the topic music. What we know from the user based on what the profiling engine has learned about them implicitly from their behavior with the experiences of the videos as seen inside the Hyper360 system is that they're mostly interested in music a lot. They're interested in music events, and in particular concerts is something that interests them. And on the right, we have, let's say, a particular 360 video that the user clicks and delves into. What we have here are 6 things, maybe 6 hotspots or links inside the 360 scenes that an annotator or an automatic process has decided what they are about. So the first one is about accommodation and something that happens outdoors. The second one is the leisure activity in a festive event. The third one is about a festival, a concert, and products inside it, or a shop maybe that's located inside a festival area. The fourth one is about a concert, the musicians in it, the artists, the stadium. The fifth one is again about a concert and music events in particular, in general. And the sixth one is a concert inside a stadium, basically. So what we want to do is to prioritize all these 6 things based on what the user wants to, what we feel the user wants to see, what we know the user wants to see. So here's what happens. For the third, fourth, fifth, and sixth content items, we determine that the user is actually interested in them in some specific degree. That is a combination of their preference and the confidence of how much we feel these things are actually inside each content item. For the second and the first one, find anything that matches the user profile, and we didn't find any contradictions, anything that tells us that the user doesn't actually want to see those things. So we ended up with a degree of 0, saying, well, it's not that they don't actually want to see it, but in all fairness, we don't find that they're significant for the user. So we're just gonna return them with an insignificant, with a degree that shows insignificance to the user. Okay, and let's put this in a little bit more context in a demo. So first we have the semantic interpreter. What we basically do and recommend for people that want to use the method to do is to train different lexical graphs for each domain or subdomain that they want to go into. This is the list of topics, domains that we've dealt through during the entirety of the Hyper360 project. So basically the reason that we want to do that is because different concepts, different words, different notions have different meanings, different semantics, maybe, potentially, for different domains. So it really makes a difference if we do domain-specific training for each particular domain. So let's see what this means in the context of, firstly, a music festival. Let's just try to classify those two words to Lumo. So we get something very, very related to music and music festivals. We have the actual words that we queried for, and some additional information about them that might be related to them in the context of a music festival. If we switch that to the very, very generic social event domain and we create there, we have a lot more information about it. So we have skirt here, which seems very weird, but since this is a bilingual English and German domain, actually the word rock also actually translates to skirt in German, and we're not constrained in the music domain or the music festival domain anymore. So this is a very valid classification for the word rock. And also you can find here that in a very generic context, apart from the specific words, the specific music genres that we're looking for, we might be interested in in music in general, and different music genres, and many more information about these things. Of course, some things are semantically insignificant since we have a degree of confidence of how much this stands. As we go down, you can see it decreases, and we can assign a threshold to cut the classification to the ones that we find more semantically significant, so something that's above 70%. Also, what we can do is, apart from mere keywords, we can take entire texts and query them to the semantic interpreter, which basically, in this particular case, that we don't have too much information, is going to narrow it down to what actually this particular part of text meant, what it deals with. Oh yeah, and I forgot to mention that the social, I mentioned it already, it can work with either English or German. In this particular domain, we trained it in both languages. And let's see something that is in English and Italian. So here we can query something in Italian for the gym and exercise domain, basically only bicycle. And what we can also do is to combine English and Italian, since we have it trained in both these languages, and get all that is related to this. Also, another thing that we can do is, if a web page publisher allows it, we can parse an entire web page. This one in particular is in Italian, and get all the information about what this web page deals with. It takes a little bit of time because it's a lot of things to process for this one. So here's basically what it was. It was actually a bike web page from the partner that that collaborated with us in this particular pilot of the Techno Gym and exercise equipment vendor. So yeah, that was basically it for the semantic interpreter and some examples about from the recommendation perspective. Here we have, let's assume these are 4 items, 2 hotspots and 2 ads, links to external web pages to ads inside the 360 video that has to do with music. The first one is a concert by Jay-Z and Kanye West. These are the metadata that came with it. The second one is again a concert of Judas Priest. These are the keywords: metal, rock, arena, and ad about specific things, products that are sold inside the music festival, t-shirts, accessories, and the fact that it's a music festival. And the last one is a particular ad for an acoustic guitar sold by the Hard Rock Cafe. The keywords are guitar, rock, and rhythm and blues. And we have several different users. Let's see, user 1, he's interested in pop and rock music. He's interested with a little less fortitude, a little less strength to songs, and even less about lyrics of the songs, I assume. And he's also interested in something compound, which is music events only if they take place in arenas. So let's try to sort out these 4 items for this particular user. We can see that the first one that comes up is ad 1 because it is clearly about rock music. The second one that he's very interested in. The second one is this hotspot, the Judas Priest concert that is about metal and rock, a concert in an arena. The third one is this hotspot that has to do with actually the lyrics is what counted more here that he prefers. But for the last one, ad 2, we don't have anything that actually matches or there is a trail that matches to these particular user preferences, so we have nothing about it here, so we return it with a degree of 0. Let's see user 3. Actually, apart from his preferences, which is again rock strongly and concerts, he hates rap, he hates hip hop, and he hates metal music, and he never wants to see stuff about those things. So what I was trying to recommend, we only get that he prefers the first ad, this one, which is about rock music. So hotspot 2, he hates rap and hip hop. We don't recommend it to him. Hotspot 1, which is about rock, comes in contrast with their specific disinterest to metal music. So we leave that out because even though it has to do with rock, we know that he doesn't want to see things about metal. And ad 2, again, is inconsistent. We don't really know anything. This leads to nothing about the user preferences. So that's basically it on a theoretical perspective. Let's just see how it works in the actual Hyper360 platform. So this is Hyper360's OmniPlayer Web. This is the web player of 360 videos. We will choose this one. This video is an experience inside the Armani Cafe. It's actually principally Italian annotated video. It's about the Armani Cafe, which I think is in Milan. And it has to do, we turn the recommendation service on. It has to do with information about all the types of products that the Armani brand has, which curiously, and I didn't know that before Hyper360, it's more than clothes and cosmetics. So now we are in the Armani Cafe video, which is primarily annotated in Italian. So the Armani Cafe has embedded a lot of links and embedded objects, hotspots that have to do with all the products of the Armani brand, which I found out in Hyper360 are not just clothes and accessories and cosmetics. It has a lot more things that we can see here in the entrance. If we click here and the Giorgio Armani logo, these are actually placeholders for links to each of these things of the Armani brand, of the different items in the Armani brand. So it has flowers, household items, I think even also furniture, sweets, the Dolce here. I don't remember what Sala is. Hotels and beauty, which is clothes and cosmetics. You will notice here that some of these are more highlighted and some of these are faded out. This is the way that our colleagues, in relation with our colleagues in engineering, we decided to show the preference. So the things that are more vivid are the ones that the user actually prefers, and the ones that this particular user, as we've understood from the system, doesn't prefer, are the ones that are a little bit faded out. Dolce in particular here, the sweets are really faded out. If we move on to the next scene of the cafe, You can see that on the tables here, you have some objects embedded. Again, these, if you click them, and I won't because it will pop me to a different page, it will show, there are links to the particular items. These ones are a lot faded out, and these ones are more highlighted because I think these are chocolates again, or something that has to do with sweets that the user doesn't prefer. These are flowers, they're acceptable, so they're highlighted a bit. And if we move, and I think also here, yeah, here these are chocolates. They're a lot faded out because we understood the user is not at all interested in confectionery. And if we move further on to the chocolate bar of the Armani Cafe, which we'll have to be patient for a little bit. So this is a chocolate bar. Let's go into a little more, another more specific view. Again, loading a little bit. There are a lot of information to go through. So these are 6 types of chocolates. These are clickable objects. If you click on them, it will pop up the particular item that it's being sold. And if you click on the particular item, it takes you to the web page where you can buy it. So as we can see, as we saw before, the sweets are not really interesting to the user. So they're a lot faded out, but this particular one is more highlighted because it's a particular thing. I don't know what it is. Let's try it out. So these are the gianducciottini, which apparently for some reason they have some a little bit more of an interest to the user than the actual chocolates. So this is mostly what I wanted to show you from the hands-on experience and how the recommendation works inside the 360 video.
So hello and welcome. I'm Hannes Fassert from Ioneer Research. I'm a senior researcher there and doing mainly video analysis with computer vision and deep learning methods. So yeah, the automatic camera path generation from 360 video. The motivation for that was already one motivation was already given by Christian, so that you can see these 360 videos also on old TV sets. The other use case is when you are seeing the 360 video on a device which supports that, but you don't want to actively explore the video. Instead, you want just consume the video in a sort of a lean back mode. So that would be the other motivation. So the goal is here, to calculate automatically a camera path, so with hard cuts from a 360 video, which covers all the important things going on in the 360 video. We are employing here several computer vision and deep learning methods for extracting the scene information. Specifically, we are doing object detection and tracking. We are using here the YOLA-4-3 algorithm for object detection. It's a very well-known and good performing object detector. And we are detecting and tracking here, first of all, the 80 MS-COCO classes. So the classes defined in the MS-COCO dataset. These are classes like person, dog, car, and several others. And the other, and we have a separate network for face detection and tracking. We are doing also human pose estimation, so the skeleton more or less. And we are using that also with a deep learning method, of course. And we are using that for determining whether persons are looking frontally in the camera. Okay, so the algorithm, just very briefly described the algorithm outline. It works iteratively, so shot by shot. We have a shot length of about 3 seconds. And for each scene object, we are calculating a set of measures. These are things like the average size of the object, the average motion magnitude, how isolated it is with respect to other objects, and the visited measure which tells us how much this object was seen in the last few shots. Yeah, we are employing now different shot types, specifically tracking shot, static shot, medium shot, pan shot, and recommender shot. And each shot type has a different style or a different characteristic in terms of the field of view which is employed, in terms of the camera motion, in terms of the focus object, and so on. For example, the tracking shot, its main focus is on moving objects which are isolated and which are bigger. For example, in a concert scene, that would be the singer of a band. Then the static shot is more focused on groups of persons, like the audience in a concert setting, and it has a somewhat higher field of view of roughly 120 degrees in order to capture the audience or group of persons better. Medium shot is sort of a close-up shot, focusing on a person's face and upper body. Then there are pan shots for exploring the scenes. And then there is the recommender shot, which is focusing on the items recommended by the recommendation engine, as presented by Dorothea. So for each of the shot types, we are generating a few shot hypotheses. And for each of shot hypotheses, we are calculating a sort of interestingness score, which tells us how interesting this shot hypothesis is supposed to be. And then we are picking the best one of this hypothesis and rendering, and we are rendering the frames from it. So from the viewport information for this shot. So here are two results given. I will show you then a demo video. So the first one is training a spotting gym, and you can see on the first row the input image, and the next 4 rows are 4 shots rendered with the automatic camera path generator. So for each shot we have here 2 frames. The other result is concert settings, music concert, and you will see that the result video soon. All right, so I will show you first how the application is running, and then a result video. Automatic camera path application it's a Python application with C++ components like the object detector and so on is running via Python wrapper. So here first the neural network for the object detector is constructed. Actually, we are using two networks for face and Muskoka. Here you can see already the object detector visualized. And in a moment, you will see the the result of the human pose estimation. So the pose estimation is done for every couple of frames. And here now you can see how all the scene objects are tracked throughout the shots, throughout the current shot. Yeah, and at the end of the shot now, when we have now tracked throughout the shot, and now we are calculating first the scene object measures, like the average rectangle size and so on. And now we are calculating for each shot type the saliency scores for each object, and the object saliency scores depend also on the shot type. Therefore, we have to do it multiple times. We are adding also a fallback shot hypothesis, which gets chosen if we don't have any real shot hypothesis. For example, if we have a 360 video where there are no persons or other objects in it, then we are taking this fallback hypothesis. And after that, we are adding shot hypothesis for each shot type. For example, for tracking, we have two shot candidates. You see, it takes some time, especially the generation of this shot hypothesis. So the automatic camera path currently is not really real-time capable. It's maybe 10 to 15 times slower than real-time. But that could be optimized. So if some of the Python code would get optimized by replacing it with a C++ implementation. Okay, so so here are the shot hypotheses added for each shot type, and then the best one is chosen. And rendered, and then this process is repeated for the next shot, and so on and so on. So now I want to show you a result video for the music concert. Unfortunately, we go to a meeting, you cannot hear the sound. So this is a tracking shot. This is also a tracking shot. This is a static shot. This is a pan shot. This is a tracking shot. This is a static shot, I think, or a medium shot. This is a tracking shot again. Pan shot. Tracking shot, also tracking. Static shot with zoom effects, tracking.
Thank you.